So today I'm going to talk about how a resilient connection can change the performance of mass timber buildings and make it um, more resilient to earthquakes. Um, okay, mass timber structures. So ever since the introduction of massive wooden panels and especially cross-laminated timber or CLT, people have started using them extensively, and in many countries around the world, but not so much in New Zealand. Almost there are CLTs overtaking the market of light timber framing. So, especially in Europe, now even domestic housing, lots of them are being made by CLT. North America as well. New Zealand is a bit behind, and we all hope that changes. CLT, mass timber structures and CLT structures, they have many advantages. They offer a high level of prefabrication, clean, fast, and cost efficient in most regions of the world, especially now that the price of the steel is going up and up. Mass timber structures have become a more feasible solution. But in seismic prone areas such as New Zealand, there is a bit of question about what's their seismic performance. Conventionally, mass timber projects are a series of panels, wooden panels, connected to each other with double type fasteners, the mechanical fasteners. So that's the conventional way of doing it. There has been, in the last 10 to 15 years, lots of research going on about to assess the seismic performance of mass timber buildings. The most comprehensive one, which I'm showing here as a representative for all of the research that was done before, is called the SOFI project, which is a 3D shake table test of a 7-story CLT building in e-defense facility in Japan. There's a short video here for the shake table test. I must ask you to please note the shakes and the acceleration, the last level of the building, which is this one. This view shows it very well. So in general, the building showed a very good seismic performance when it was subjected to severe design level and above earthquakes. The observation from this test was that the maximum values of uplift, interest, or slip of vertical in-plane joints of wall were not critical, so generally a good performance. Failure mode was ductile with fastener bending and embedment, which is also good. But there were slackness in the hold downs on bolts, and surprisingly, a very high acceleration at the top, around 4G. And you can see that many of the connections were damaged. So in a country like New Zealand and Japan, that we have lots of aftershocks and earthquakes, is this enough for like a one-off good performance? Is it enough? The answer is no. So the main takeaways from the SOFI project and many of other researchers, we need resilient connections to be able to have a seismic resistant, or in New Zealand terms, low damage mass timber structure. So we need energy dissipation because of the nature of these buildings. We will note very high acceleration. So I'm going to talk about the resilient slip friction joint from research to practice. It is a technology that was developed from research at the University of Auckland and later on University of Auckland and Auckland University of Technology. This technology, this solution was developed to address the shortcomings from the previous research around mass timber structures and the two key points that I discussed, resilient connections and energy dissipation. So what it is a connection that dissipates energy and also provides self-centering. The energy dissipation is based on a combination of frictional movements and semi-compacted discus springs. And you can see in this video how it behaves. The main characteristics of this connection or this solution is that it's a friction damper that's self-centered. Behavior is geometrically nonlinear, but it's not plastic. There is no damage up to the design level load and is applicable to all materials and all types of lateral load resisting systems for new and retrofit buildings. For timber structures, cost effective because the ductility and damping you get from this is not comparable with the ones you're getting from conventional solutions. It doesn't need any maintenance. It can be monitored. It's compact, it's flexible, and it's very easy to install. So all of these were considered when the solution was being developed in 2014, 2015, University of Auckland. Before we continue, a note on why we need self-centering. There has been research and field studies in different countries around the world that if the residual drift ratio is more than 0.1%, probably the structural members should be realigned. And this was a key observation from Christchurch. And also the overseas studies show that if the residual drift ratio is more than 0.5%, reconstruction may be more economical. So recentering is an important aspect of design. How does it work? So it has a sliding plates that are grouped and form valleys and ridges, and in combination with discus springs and high strength bolts, it combines the resilient slip friction joint. So the key point is that the bolts only work in tension, so bolts are not in shear, the clamping bolts. And it's designed that the plates can jump to the next level, to the next groove. And at maximum capacity here of the joint, the discus springs are fully compacted. Also, there is a gap between the orange plates that allow for compression movements as well as tension movements. So it's a tension compression. The hysteretic or the load deformation behavior of this connection is a flag-shaped one, means you will have zero force and zero displacement or a self-centering characteristic. There are multiple parameters within the device itself to be used and to be tuned. So all different hysteresis types are possible. So this gives a great deal of flexibility to the designer to be able to apply the required flag-shaped performance to be able to achieve the target performance objective. Overstrain mechanism. So we have been receiving the question that what will happen when the device reaches the end? Does it lock? The answer is no. We developed also a secondary fuse or overstrain mechanism in a way that when the When the devices are at their max displacement, these bolts yield in tension. That means that if the event was larger than a design level event, the bolts will yield and they have to be replaced. This has been tested at the University of Auckland. As you can see, this is one of the tests. So for this one, the joint was designed for 8 millimeter displacement, but it could go up to about 2 times of the displacement with these clamping poles yielding. This is another one which is very recent. This device, the specified characteristic was 375 kilonewton this point at 60 millimeters. So this was the design. So this was the design or ULS specification for this device. And this is the overspring mechanism. As you can see, the device was designed for 60 millimeters, but it could go up to 100 millimeters with this increase in the force from about 375 to about 450. Dynamic performance. When we were doing the research, we were asked what will happen to the device if it's loaded rapidly. Does it change the specification? So we performed a series of dynamic testing to make sure that we're not compromising on the performance. So with the test I'm showing you, we did, instead of doing appropriate loading protocol, we did about 25 full cycles to push it to see what will happen. So 3 different loading rates we used. This is the quasi-static or the slow one, 1 Hertz frequency and 2 Hertz frequency. As you can see, the performance is quite stable and about 5% increase in the resistance of the device we observed. Okay, considering this overstring mechanism and considering dynamic effect, the minimum overstring factor of 1.35 is applicable for this system, which is in timber world is very good because normally the overstring factors we work with for like plywood shear walls or other nails or others is about 2 or more. So this provides a bit of saving on that front. Potential applications. As I mentioned, this solution is not so our presentation today is timber focused, but as I mentioned, the applications of this technology is not limited to timber or a specific type of lateral system. So quickly here I go over different applications. It can be used as intentionally braces. So as you know, we don't have ductile tensionally braces because tensionally braces are normally there to provide ductility of 1 or 1.25 at most. And because the reason is when they yield, the lateral system is basically gone. That's the point of difference from tension compression braces. And most of the standards around the world restrict the use of tensionally braces to 1 story or 2 stories. But with the resilient and slip friction joints connected to a tension member, we can have a ductile tension-only system. So with basically the connections can be connected to a tension member, can be a rod or reed bar or whatever, and then attach it to the gusset plate to display a ductile behavior. This is one implementation that happened last year in Wellington, a retrofit. Another one is hold down for rocking shear walls. So rocking walls are becoming more and more favorable, especially in timber world when we have wooden panels, like CLT panels, coming on site and ready to be attached to the foundation. So by use of rocking walls, we can easily have a large ductility and damping and save on fasteners and other fasteners, timber, and foundation. With these ones attached, used as hold down, there is no need of using post-tensioning cables up the height of the wall. So yeah, so it's just that for shear key, it's just a matter of detailing some sort of shear key for the wall. I mentioned the technology is material independent, so it doesn't matter if it's timber, concrete, or even a steel shear wall. For braces, so for tension compression braces, these devices are used in combination with a telescopic mechanism to take care of global buckling of the brace. Normally, there are male and female parts that go into each other, and then a mechanism similar to that of a BRB, buckling resistant brace. And yeah, here you can see the female part and the male part. These are in parallel with the resilient friction joint to form a resilient brace. So for timber braces is the same concept, but we will have steel telescopic tubes in this form. So we use steel telescopic tubes in parallel with the devices, and all of them, the assemblies attached to the timber member using different layout and different connections that I will describe later when I'm talking about the case system. It also can be used in moment-resistant frames. I have a render for steel application, but basically there are projects that this is being installed for timber moment-resistant frames. So they can be used as a top chord or bottom chord when required to form a resilient moment. Okay, so after a quick look at the applications, I'll describe the research that was done from 2015 onward, and then we jumped into practice, implementation, and then a few final notes on design philosophy. Research started by this one. This is the very first full-scale one that was tested at the University of Auckland. At that point, we wanted to make sure it works. It worked beautifully. As you can see, the results on the right. Flash-shape performance, fully self-centering, everything that we expected. And then the first larger scale test that was done was on a CLT wall, where the devices were used at the two bottom corners, representing hold downs for rocking CLT shear wall. And the result we received was perfect. So this wall didn't have any gravity load or tensioning, but the performance was self-centering regardless. A short video from the test. For this test, plus or minus 3% of drift was induced at the top of the wall. The system performed well. We didn't notice any damage in the wall, in the connections, or anywhere. Excuse me. This is an experiment that was done on a 1,000 kilonewton unit. It was later installed in the Nelson Airport terminal, which I will describe later. You can see the movement of the plates and the compaction of the discus springs. This was also done at the University of Auckland. In-plane and out-of-plane testing of a rocking LVL wall where the units were being used to hold them. On the left, you can see the in-plane performance, and right, you can see the out-of-plane performance. For the system to be able to accommodate out-of-plane movement, a swivel bearing, a spherical bearing, is used at the bottom of the device to make sure that it's a pinned assembly for in and out-of-plane connection. The next test I'm going to show you is a tension-only brace strength test, University of Auckland. So as I mentioned, there are not lots of ductile tension frame, but basically this is actually one of the few ductile tension frames in the world. This test was dynamic. At the left, top left, you can see the real-time result. For this one, we use the load protocols and the frequencies recommended by ASC 7, and we induce 5% drift to the steel frame. And as you can see, a very nice behavior, fully flat shape, repeatable, without damage to the tension members or to the devices. Next one at the AUT is the timber brace. With the assembly that I showed you before, devices and anti-buckling telescopic tubes attached to the glue lamp using gluing rods. And this is a very short video from the test. This test was also dynamic, so the video is not dynamic, but this is one of the initial tests, but test was dynamic, and this is the dynamic performance. As I mentioned, the behavior is material independent, so I thought I'd just prove this as well. A rocking concrete wall, which is no different from a rocking CLT wall. Same level of performance, which is tunable according to the objectives of the project. Lastly, dynamic testing of a steel brace where two of these connections are used at the two ends. So this is normally required when there is a huge displacement requirement. The noises you hear are not from the devices or the brace, from the test setup. Okay, after going over the applications and research, let's look at case studies where the technology was implemented. Nelson Airport Terminal was the first one, all timber building designed by Donnie Thornton in Nelson. So for this one, resilient friction joints were used at the bottom corners of LVL columns at the base, and for some of them at the mid height to provide a double or single rocking mechanism. So the tests for in and out of plane testing that I showed you before was actually for this, because this was the first project. Full-scale testing of the column was also a requirement that was done at the university. You can see some photos here. So by using this technology, And the ductility introduced to the project, a significant reduction in the member sizes and connections were observable. The next project is the Hutt Valley Health Hub, and next case study is the Hutt Valley Health Hub in Wellington. For this one, timber braces in one direction and rocking concrete walls in the other direction was used. The building intended to be an all timber building, but the CLT couldn't be sourced in time. So the designer decided to change, the CCW Nelson decided to change to concrete walls, which basically same concept. So this gives you a good view. K-braces, 7-5 braces in one direction, walking concrete shield in the other direction. The brace test that I showed you a few slides back at AUT was related to this project. More photos. The designer, so this was an IL4 building, and the designer was able to achieve ductility of 2 with all the SLS1 and SLS2 requirements. Close view of the devices and telescopic mechanisms. So these telescopes are designed in a way that can have a similar stiffness to that of a brace body to be able to control the global buckling. Next case study is the Christchurch Cathedral College, which for the ones who attended the CSOC conference in Hamilton just recently. WSP Christchurch designed this, did a great job, and won the CSOC Supreme Award. This is a panelized building, all timber panelized building, which devices were installed at the bottom of all CLT walls to provide a rocking mechanism for in and out of plane direction. So the displacement ductility I see for this building was about 8, and the equivalent ductility was about 2, if I remember correctly. As mentioned, swivel bearings. There are swivel bearings at the bottom, so they can, a pin assembly for in and out of plane is provided. Now I want to move into case studies overseas in Canada. Before I start, I just want to show you the Vancouver hazard because not many of us know how demanding is earthquake in North America, in Vancouver. So Vancouver is very demanding in terms of earthquake. It is something between our current Wellington and current Christchurch. So close to our demand and require the same level of attention to connections for mass timber structures. Fast+Epp head office was the first building in North America, well, outside of New Zealand, that implemented this technology. All timber building that uses CLT rocking shear walls as lateral logarithmic system. For the ones who attended Andrew's webinar, he probably talked about this a lot because he was the main designer of this building and did a great job. For this one, devices in the range of 700 kilonewton was used as hold down for rocking CLT walls. And this shows the installation sequence here, that the devices installed first, and then the panels were put in place, which was the other way around for the Cathedral College project in Christchurch. For those, the panels were there with dummies representing the devices, and then the devices were added later. This building, ductility of around 2 in New Zealand terms were achieved. It could be pushed to more, but the designer wanted to keep it in that range. To connect, this detail could be interesting, how to connect the units to the CLT. Normally in North America, it's very, they're very comfortable by using knife plates and then using dowels. But in New Zealand, there are different solutions. This is not that common. I hope it becomes more common. And gluing rods are common in New Zealand, have been used in some projects. Cathedral building, Vancouver, a 10-story building. This one is in tender now, was paused because of COVID. This is a landmark project. It's the tallest all-timber project in a seismic active area. The lateral system is braces in one direction, and then combination of braces and rocking walls in the other direction. So the design approach was a performance-based design. It was deemed as a special project. A New Zealand solution for the tallest all-timber building in a seismically active region was used. It was a collaborative and iterative design process between 4 different parties. It had 2 peer reviewers. It had 1 peer reviewer just dedicated for the analysis, selecting their quick records and scaling them. And it had a second peer reviewer dedicated for structural design, detailing, and performance. Kind of a big deal, because it was outside of every code and standard they have in Canada, and I think same here for New Zealand. For the ones who are curious how they do in Canada, how they do time history, so they pick 15 records, and then they run the analysis. They select they identify the 5 worst ones and then average them. Here we mostly use a max of 3, so there's a difference here. Designer's intention was to keep the intra-story drift under 1%. The ductility related reduction factor of RD of 3 was achieved, which is equivalent to our KMU in New Zealand. Fully self-centering behavior because of the RSFJ, and also the overstrength factor of the RSFJ was considered as enough for MC performance. These are the details they used to for the RSFJs and the braces. So they had devices and anti-buckling tubes pinned to the gussets, and then using the similar knife plates inside the glue lamp, and then using dowel to connect. For the walls, an interesting and sort of innovative detail was used. RSFJ hold downs in the form that you see were used at the bottoms. Instead of a rocking mechanism, they selected a rotating mechanism. And this rotating mechanism allows to eliminate the uplift demand at the wall-to-floor connection, so basically reduce the damage. And then as a secondary mechanism, they had yielding perforated plates between, so it was not a single wall or a segment, and between the segments they had perforated. So during large events, RSFJs will activate, and then as a secondary mechanism, these will yield a robust system. The other one, the last case study is the ON5 Building in Vancouver. Similarly, a rocking mechanism was used, gravity system was COD, and also lateral system. Analysis was performed in Drupal and ETABS, pushover analysis using 2 load patterns, acceleration base, and display the load vector was performed to come up with the So here you can see the capacity spectrum of the Vancouver and then the two pushover analysis with the two load patterns that was performed. So one thing is that FEMA 356 was used to design this building, which is very similar to our part C2 of our retrofit book. So basically, same thing, same principle. Similar detailing was used to connect the units to the CLT, knife blade, and dowels, which is like bread and butter in Vancouver, but is kind of considered as a crazy detail somehow in New Zealand. I hope that changes soon, well, near future. And there are some recent photos from installation and erection, which I think it was last photos were taken the last 3 weeks. About the design, I'm going to talk about how to start the design, but how to finish it depends on the complexity of the project and also designer's preference. Damping ductility relationships are developed for this system, which is available, published as an ASD paper. So this is damping ductility relationship for this system and any other self-centering system. If that's too complicated to use, then area-based method also can be used to calculate damping of the system. Many of us are familiar with the capacity spectrum method. Basically, it talks about adding the acceleration spectrum and displacement spectrum together. The acceleration, displacement, response spectra, or the ADRS curve. ADRS curve can be scaled down based on the damping we have in the system. The formula to scale it down, which is in Nigel Priestley's book and many other resources, is based on Eurocode 8, and it's this one, which hysteretic damping and elastic damping are used. Scale down the ADRS, ULS ADRS. Also, we have our SLS, which these devices don't expect to perform under SLS1 or even SLS2. That depends on the designer's preference. So we don't scale it down. Then we decide about the drift before device expansion. So SLS1 is normally 0.33% in that range because the structure is expected to behave elastically. And then at full expansion, although we are allowed to go to 2.5%, but we normally, for a low damage performance, we keep it 1% to 1.5%. Intersections with the acceleration can determine our base here at ULS and SLS. Using R sub J design equations, we can form the full loop and we can calculate the damping and verify with the assumed damping. So this is the iterative procedure. It's a very, very good approximation to start the design. But to finish this, it all depends on the preference. I'll talk about it in a bit, but a general note on design philosophy. The activation, well, conventionally known as the yield, well, in this case, it's not yield, it's flip, is the point that normally we use for SLS because we don't want devices to be activated at SLS1. So that's easy. This region, which is the post-slip positive stiffness of the building, this can be used for SLS2, ULS, or MC. So this point, which is the end of where the devices are at their maximum capacity, doesn't need to be necessarily ULS. ULS can be here, 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 here. That depends on you as the engineer, how conservative you want to be, okay? And the technology is quite flexible in that regard. this portion, the last portion, which where the rod yield or the post elastic region, where we will have minimal control damage. This is normally used for MC and beyond. So this is the overstring mechanism. Maybe one of you say, okay, I'm too conservative. I want my MC to be here, not QLS. I want elastic behavior up to MC. Then the overstring mechanism will be activated after that. Okay. So the my intention to show this slide was to show how flexible is the system. It all goes back. There is no must here. It all goes back to your design philosophy. Thank you for listening to me. I think I managed to finish in 40 minutes on time. And I'm happy to answer questions if there are. Thank you.
Thank you very much, Ashkan. That was really very impressive talk. Very good effort and experimental part of testing materials for seismic design. We have a list of questions, not that much, but which is good that you can be able to answer all. First one coming from Carlos, saying, can you provide a range of cost for those devices? Do you have a range of price in dollars per kilonewton for an engineer quickly have a glimpse on the cost while in the analysis stage? Thank you.
Well, yes and no. So it's easy. I think firstly for timber structures, our experience showed that this is cost positive compared to conventional design. But if you're after a cost of a certain capacity, we can get in touch with the company that commercializes the technology. I think they'll be able to answer you fast.
Okay. The second question coming from Anonymous, can a ductility greater than 2 be assigned to CLT shear wall structure with RSFJ?
Yes, that's easy. The reason that the ductility was around 2-ish for the previous project was just the engineer's preference. But there are projects now, the ductility is 3.5 or in that range or close to 4. That all depends on your design and how do you want to process.
Okay, next question coming from Anne. Are the CLT panel connections available commercially in New Zealand?
If you're talking about the knife plates and dowels, yes, I think dowels are standard rotoblast dowels, and the knife plates can be fabricated in New Zealand. It's just a matter of us having the confidence and knowledge to specify. I think they're available.
Okay, next question, Anonymous. For the Fast+Epp buildings RSFJ hold down, how can we accommodate the tolerance for installation? I would assume the tight fit double holes in CLT were pre-drilled in factory and are not adjusting on site. Any measurement in RSFJ for installation tolerance? Thank you.
Normally the installation tolerance is about 5 mil plus minus, actually -0 plus 5 mil, and that is for hold downs is easy. That can be done by shims. Sometimes grouting, but shims are mostly enough, and they contractors successfully did that.
Okay, next question coming from John K. In the case of timber CLT walls acting as rocking walls, how can we reduce the risk of compression, buckling, and the wood?
I could not get the question where exactly you are referring to compression in wood, but I can mention one thing, that the wood is capacity designed. So whatever is the action in the device times the overspin factor will be used for the wood to be checked for everything, and everything, shear, tension, buckling, compression, everything.